Greetings, ladies and gents, and welcome back at Mike Maths and Science Club. In this video, we'll be looking at a question, at question 4, which was on a paper which was written in November 2022. It's a question on momentum. So they said that trolley X of mass 1,2 kg travels at 8 meters per second east and collides with trolley Y of mass 0,5 kg, which is initially at rest. So we know that, of course, the velocity of trolley Y initially would be 0 in this case. So they said that ignore all frictional effects. They said that the velocity time graph below shows the velocity of trolley X before, during, and after the collision with trolley Y. So in this case, if we look at this diagram that of course they gave us, we know that of course initially, as they stated, they said that of course the trolley X was actually moving at of course 8 meters per second, right? So this would be before, right, the collision, and after the collision, of course, the velocity of that trolley X is still in this case it changed to 4 meters per second. So in this case, of course, this portion here that we have here, this would be in this case the time taken over that collision took place in this case. So in this case, they said that for 4.1, of course, there is another question that we have down there, but which is of course just one question. So in this case, that's the other one. So in this case, I would advise that you just pause the video, and then of course you try it, and then of course you watch the solutions afterwards. So in this case, for 4.1, they said that this stated the principle of conservation of linear momentum. So we know that of course the principle of conservation of linear momentum states that in an isolated system, the total linear momentum before collision is equal to the total linear momentum after collision. So in this case, that would be of course for 4.1. I'm not gonna write that down unfortunately. So they said that for 4.2, calculate the magnitude of the velocity of trolley Y immediately after collision. So now one thing I can say is that when they ask you of course to state this principle of conservation of linear momentum, surely in the next question you'll be required to use that law. So in this case, we know that of course what the law that we're going to use here for 4.2.1 would be of course the principle of conservation of linear momentum, which state that of course we know that of course EP before initial is equals to sum of EP of P final, right? So in this case, it would be a final. So in this case, of course, if we expand that, you can, I'm sure you can note, of course, that we have two trolleys, right? Trolley Y and, of course, trolley X. So what I'm going to do would be, of course, to expand that equation there. So in this case, I know that, of course, this would now, how we calculate momentum, we know that, of course, momentum is equals to mass multiplied by velocity, right? So this would be M V, right? So that would be for trolley X. So this would be initially, right? But for trolley X, right, plus MVI in this case for trolley Y. So this will be equals to MVI, VF rather, but in this case for trolley X again, plus MVF, but in this case for trolley Y. So in this case, so what I'm going to do now, the first thing that you must do before you even start, your calculations would be to choose which direction you're going to consider as positive. So what I'm going to do, I'm just going to consider going to that side. In this case is positive. Going to the right, in this case is positive, which of course you would consider as east, right? So in this case, I'm gonna take of course going west is negative. So in this case that would be plus, and that would be minus. So in this case, of course, the mass for trolley X, as they said, that was let me just scroll up. So they said that was 1.2. So in this case, I know that of course the mass is 1.2. So this would be 1.2. In this case, I know the velocity. In this case, I know that initially it was traveling to the east, right? So that's what they stated in the statement. So in this case, I took, of course, going to the right or, of course, to the east. Let me just write this. Let me just say east. Right, that's positive, and of course, going that side would be west. Right, so in this case, I know that of course east I considered this positive, so this would actually be an positive 8. Right, so always put it into brackets. So in this case that would be plus the mass of trolley Y, which was 0.5 if I'm not mistaken. Let me just scroll up again. So in this case that was 0.5. So in this case I know that of course this is 0.5, right, multiplied by 0. They say that of course it was initially traced, right? So in this case this would be 0. So in this case, of course, after the collision, we know that of course trolley trolley X rather, it was moving at 4 meters per second, right? Of course, in the same direction. So in this case, of course, we know that of course the mass still is the same, so that would be 1.2, right, multiplied by its velocity, which would be 4, right, and then of course that would be plus the mass of trolley Y, which is 0.5. Its velocity, it's what we don't know right now. So in this case, I'm just gonna leave that as VF X. All right, so in this case, what you're going to do now, and of course this thing is actually going to give me 0. So what I'm gonna do, I'm just gonna do the additive inverse of this. I'm just gonna take it to the other side. So in this case, it's gonna become negative. But yeah, of course, so we know that. So in this case, this would be 1.2, right, multiplied by 8, plus 0, and minus that 1.2 multiplied by 4. So this would actually be equals to 0.5 VF, in this case for X. So what I'm going to do in this case would be to divide everything by 0.5. So in this case, I'm going to divide everything by 0.5. So I'm just going to divide everything by 0.5. So in this case, that would be 0.5. So of course, if I do that, of course, this would actually cancels with that. So this cancels with that. In this case, I'm only left with VF for that trolley X. So in this case, let me just scroll up again. So in this case, what we have in this case would be VF being equals to, let me just take the calculator there. So in this case, we have 1.2. So in this case, this will be 1.2 multiplied by 8 plus 0 minus 1.2, in this case multiplied by 4, and then of course we divide by 0.5. So in this case, what we have is the velocity of that trolley X would is actually that 9.6. So in this case, we know that VFX would be 9.6 meters per second. So that would be the SI units, of course, for velocity. So of course, what you need to note here is that they actually asked for the magnitude, right? So we're not going to concern ourselves about the direction of that velocity. So for 4.2.2, they say that calculate the magnitude of the average net force that trolley X exerts on trolley Y during the collision. So we know that, of course, in this case, the time taken over which, of course, those objects were in contact was actually that. So this would be the time. So this would actually be the time there. So in this case, you just take the difference between those 2 points. So in this case, this would be the time after collision, right? So that was before. So you know that, of course, the time taken over which those two, of course, objects were in contact. In this case, during collision, that was actually 0.1. So in this case, 20.2 minus 20.1. So that actually gives us 0.1. So in this case, I know that, of course, time, that would be 0.1. Right, so in this case, to calculate that average net force, what we would do in this case would be to use the equation which says that F net. Let me just scroll that. So this is, this would be F net. So in this case, that would be for answering for 4.2.2. So that I would use, of course, the equation that says F net multiplied by delta T is equals to the change in momentum. So in this case, I'm just going to take, of course, the information that I have about trolley X. Now, of course, if we didn't have any information on trolley X, we're just going to use, of course, the information that we have on trolley Y. Why? Because in this case, I know that, of course, the force exerted by trolley X on trolley Y, that would actually be the same force that, of course, trolley Y exerts on trolley X. So in this case, the difference would be, of course, in the direction. So now remember that, of course, we considered going to the east as positive, right? So what I'm going to do, I'm just going to expand this formula that we have here. So in this case, we still have F net multiplied by delta T. So this would simply be equals to, of course, M V final minus M V initial. So this would be, of course, for trolley So that would be for trolley X rather. So that would be for trolley X. So of course, let me just write that as X there. So that would be for trolley X. So in this case, what we do, of course, we're looking for F net, right, in this case, but we know the time, right? So in this case, the time would be that 0.1. So we know that, of course, F net multiplied by 0.1, that would actually be equals to the, of course, the change in momentum of that object. So in this case, we know that, of course, the mass was 1.2, so this would be 1.2 multiplied by its velocity. So in this case, it was traveling towards east, right? So in this case, that was 8. All right, so that was 8. We subtract the mass again, that's 1.2 multiplied by its so in this case, that was supposed to be final rather. Let me just erase that. Forgive me about that, ladies and gentlemen. I'm actually thinking that that was actually the final velocity. So in this case, we know that, of course, the final velocity was 4. So in this case, the initial velocity in this case was 8. So of course, what we're going to do in this case, F net will simply be equals to 1.2 multiplied by 4. All right, minus 1.2. Multiply that by 8, and then of course we divide everything by 0.1. So in this case, F net will simply be equals to, so let's just take our calculator again. So we have 1.2. So we have 1.2. Just put that into brackets. So we have 1.2 multiplied by 4 minus, in this case, 1.2 multiplied by 8. So in this case, we divide everything by 0.1. So this is what we have would be, of course, the F net being a negative 48. So that would be negative 48. So in this case, since they asked for magnitude, so in this case, that negative, it interprets, of course, the direction, right? So in this case, what would have would be, of course, F net being equals to so that would be equals to 48 Newton. So that would be for 4.2.2. So in this case, for 4.2.3, which is the last question, so in this case, that's actually 4.3. So they're asking that is the collision elastic or inelastic? So in this case, we're supposed to prove whether a collision, of course, is inelastic or elastic. So what you would do in this case would be to calculate the sum of the kinetic energy of the system before collision, and you calculate the sum of the kinetic energy after collision. So if of course you find that of course the sum of the kinetic energy of the system before is equal to the sum of the kinetic energy after collision, in this case, if they're equal, then you would know that of course this is an elastic collision, right? But if you find that they are not equal, so in this case it would be an inelastic collision. So what you're going to do, you're not going to equate them first, but in this case you're going to to calculate the sum of the kinetic energy before collision separately, and then you calculate of course of after separately as well. So what I'm going to do, let me just scroll down again. So in this case, what we have would be, so in this case, we know that of course, I'm just gonna say that, let me just take another color there. So of course, what we have would be sum of AK being equals to a half mv squared, for this is for trolley X, plus half mv squared for trolley Y. So this will be for Y, for trolley Y. Right, so in this case, what I'm going to do, I'm just going to calculate the sum of the kinetic energy of that system before collision in this case. So this would be initially. So in this case, I know that of course this would be half, and this is the mass of course of trolley X was 1.2, right? The velocity was 8, right? So we square that, plus a half the mass of trolley Y, that was actually 0.5. So that's 0.5. So this will be 0.5. And then of course the velocity was actually 0, right? So this whole thing is actually 0. So we square that. So if you put that into the calculator, let's see what we get. So we have 0.5 multiplied by 1.2. Right, 1.2 in this case multiplied by 8. We square that, plus, of course, we know that's a 0 there, so you actually get a value of in this case 38.4. So in this case, we know that of course the sum of the kinetic energy of the system before collision was actually 38.4 joules. Right, so in this case, what I'm going to do, so in this case, that was for before the collision. So in this case, for after collision, so in this case, we say that, of course, this is for before. All right, so in this case, for after, in this case, I'm just going to calculate, of course, the sum of the kinetic energy of the system after collision. So I'll say sum of EK, in this case, final. This will simply be equals to half mv squared of trolley x plus, in this case, sum a half, of course, m v squared of course of trolley y. So in this case, this will simply be a half the mass that was 1.2 multiplied by its velocity, right, which was actually 4. All right, so that was actually 4. Just so this would be 4, but we square that plus in this case, I'm just actually checking if I actually squared that. So in this case, what we have would be force plus a half. The mass would be 0.5. In this case, of course, the velocity, we found that to be I think that was 9.6, if I'm not mistaken. Let me just scroll up so that I don't make silly mistakes. So that's 9.6. So in this case, so I wouldn't actually concern myself about the direction of the velocity, because anything squared would actually just give you a positive number. So in this case, we said that's 9.6. To square that, let's just put that into the calculator. Let's see what we can get. So in this case, we have 0.5 multiplied by 1.2. 1.2, we say 4, we square that, plus 0.5. In this case, that would be 0.5 again, so that's 0.5. Multiply that by 9.6, so that would be 9.6. We square that. So in this case, what we get would be, of course, 32.64 joules in this case. So of course, we found that, of course, the sum of the kinetic energy before collision is not actually the same as the sum of the kinetic energy after collision. So in this case, since we know that, of course, EK before, in this case, since we know that, of course, EK before, EK, so this would be for after, right? So for, let me just write the after collision. So we know that, of course, since, of course, the sum of EK initially is not equals to the sum of EK final. So in this case, we know that, of course, this would be, of course, an inelastic collision. I just hope my spelling is right there. So in this case, we have, of course, concluded that, of course, this is an elastic collision. Of course, why? Because we know that, of course, the sum of the kinetic energy of the system before collision is not equal to the sum of the kinetic energy after collision. So in this case, we know that, of course, this is an inelastic collision. So this is it for today's video. And of course, if this helped, be sure to like the video. And of course, if you haven't subscribed, be sure to subscribe and hit that notification bell, because there are actually more videos to come. So in this case, as the story always ends, ladies and gentlemen, this is Mike signing out. Sharp, sharp.